In this video, we will talk about system calls. Uh, they are essentially an interface between the user process and the operating system. In other words, system calls provide an interface to the services made available by an operating system. Let's take a look at a diagram on the right over here to see why we need them. So over here we have the user space right at the top in red. Underneath that we have the kernel space, which is a privileged mode, and underneath all of this we have the shared hardware resources. So for example, if a user process that is currently running in the user space, if it needs to directly access hardware resources, that's not possible. Only if a process is in the privileged mode, it has direct access to the hardware resources. So what can a user process do if it needs direct access to the hardware resources? Well, it needs to use one of the system calls to be able to transition to the kernel space, and then now that it is in the privileged mode, it can access the hardware resources. So that's essentially how we are using the services of an operating system, but at a user process level. These tools are generally available as routines that are written in C and C++ or assembly language. They are equivalent to a software interrupt. And this is a mechanism for operating system to provide such services. There are three ways to pass parameters between a process and the operating system. It could be in the form of registers, as a block or table in the main memory, or on the stack. We can classify system calls into 6 different categories. The first one is the process control type of system call. So in the process control system calls, we have all the calls that are directly related to the process itself. So for example, ending and aborting a process. So we would want to end a process normally, and we use the system call end for that. And if there's a halt or abnormal end to a process, we use abort for that to indicate that. We we use load and execute system calls to load a process and execute a process. We use create and terminate system calls to create and terminate a process. Um, we could a process could may need to wait for an event or signal an event. So those are the two system calls for that. And if a process is ready for execution, we definitely need to allocate some space in the main memory so that the process can start executing. So we need execute, and once it is done, then we need to free up that particular memory space. So we have the allocate and free memory system calls for that. The next category is the file manipulation. So all the system calls in this will be relevant for a file, for a particular file. So this could be file management or file manipulation type of system calls. So to create and delete a particular file, to open and close a file, to be able to read and write or seek in a file, and then to get and set file attributes. So these are the system calls that are that fall in this category of file manipulation or file management. Following that, we have device manipulation. So in case the process that is currently executing needs to interface with a particular device, then we need all these calls to be able to interact with the device. So to be able to request and release an IO device, for example, to be able to read and write and seek to a particular IO device, to be able to get and set device attributes. Following that, we have logically attach and detach a particular device. So this is sort of different from physically attaching and detaching a device. You definitely have seen whenever you plug in a USB flash drive to your computer, that is when you actually plug it in, that's a physical attach and detach when you remove it. But when you plug it in, the operating system needs to recognize that particular device, and that is what we call logically attaching the device. And once you are done using the USB drive, you usually click on an icon and say safely remove hardware button. Before you actually physically remove it, you logically detach it first. Um, and then the next level is your information maintenance. So all the information regarding time, date, your system data, and the process or file device attributes, those could be get and set using the information maintenance type of system calls. The next category is the communications. So if processes need to communicate between each other, or a process needs to communicate with a device, we need a certain system calls to make that happen. So for example, we have create and delete connection between processes or devices. We have send and receive messages between two processes, for example. We can transfer status information. So for example, if a process is finished execution, then it can let the other process know by transferring its status information. And we can attach and detach remote devices using these specific category of system calls. The last category is the protection system calls. So this is to set or modify permissions for a particular process. On the slide, we see examples of Windows and Unix system calls that are for each of those types of system calls. This is mainly for your reference. Note that we are going to look at fork, exit, wait, and exec Unix system calls in this lecture in the next part. Now let's focus a little bit deeper into the process state diagram. So what are the different stages a process goes through in its lifetime? So a process may go through many states during its lifetime. So for example, all the ones that are circled, these are states. So they are, in this diagram, we have 1, 2, 3, 4, 5 different states that are indicated for each process. So what does the new state mean? Well, if a process is newly created, then it will be in the new state. So it is just created here. So let me write that over here, created. Then once it is created, we would need a processor to be able to start executing that process. So we admit that to a new state called ready, where it is going to wait for a processor to start working on it. So that's the ready state. Ready state is when the process is ready to for a processor to start execution. Then the scheduler dispatches it to another state, which is the running state, in which it has obtained a processor. It is right now currently executing instructions in that particular process. So a scheduler dispatcher is responsible to assign a processor to that particular process. Once it is done, it is in the running state. And from the running state, several things can happen. So for example, if the process completes or terminates, it exits and it is the next state, which is the terminated state. Or if there is an interrupt, then the running process is going to stop and go back to the ready state, and then again wait for another processor. So that's your interrupt. Or it might wait for a particular IO operation or an event to occur. So when it is waiting or when the running process is waiting for an IO to complete or event to happen, then it will be considered as in the waiting state. Then once the IO or the event is complete, it goes back to the ready state, where again it is going to wait for a processor to start working on it. So those are your different states, and essentially the interrupts are driving them from one state to the other. Now, as you can see, usually this will go new, ready, running, and terminated. But if you have interrupts, then it may not terminate. Before it terminates, it might go to the waiting and ready state again. Okay, so those are your process states. Let me highlight this process state. And as you can imagine, each process will be in one of these states at any given time. Next, we start talking about process control block or PCB. And each process will have one process control block. And there are lots of information that are specific to a particular process that are embedded in that process control block. So for example, it might contain a process ID or process number, which is a unique number to identify that process. It might contain the process state, which means that's the way I would know whether it's a new process or it's a ready, it's in the ready state or it's in the running state. So the state that we just looked at in the previous slide, that is going to be part of the process control block. Then the next thing that is in the process control block is the program counter, which is essentially the address of the next instruction that is going to be executed in that particular process. Then you have the CPU registers. This could be stack pointers. This could be general purpose registers that the process is currently using. After that, the process control block also has CPU scheduling information. So for example, the process priority is something that goes into this CPU scheduling information bit. Then there is information on memory management. So this includes the value of the base and limit registers that we saw in the previous lectures. Then we have accounting information, which includes how much CPU is the process using, or the job or process numbers that the process is using. Then at the end, we have the I/O status information. So if a process is currently interacting with a I/O device, that status is also part of the process control block. And because process state is a part of the process control block, it gets updated after the process has a change of state. So now let's see how we keep track of the process control blocks. So to meet the objectives of multi-programming, which is still have some processes running at all times to maximize the CPU utilization, or to meet the objectives of time sharing, which means to switch the CPU among processes frequently, the process scheduler selects an available process for program execution on the CPU. Now this involves the maintenance and scheduling of jobs from different types of queues. We have over here a job queue, a ready queue, and an I/O device queue. A job queue consists of all the processes that are in the system. A ready queue consists of all processes that are residing in the main memory and are ready to execute. So for example, over here we see a ready queue where PCB 1, process control block 8 and 25 are ready to get executed and are currently residing in the main memory. The device queue or the I/O device queue contains the list of processes waiting for a particular I/O device. The queue is generally stored as a linked list. The head of a queue contains pointer to the first process control block in the list. The tail contains the pointer to the last PCB in the list, and each PCB includes the pointer to that points to the next PCB in the queue. So PCBs go from one queue to the other. All right, that's it for this part. Next we start talking about the process creation and the fork system call.